Hello students, in this video we'll find the formula for the Riemann-Christoffel tensor in two-dimensional setting. So let's consider the metric ds squared is dx squared plus g of xy quantity squared dy squared. That's a two-dimensional metric. In compute, let's compute r of 1, 2, 1, 2. And that will allow us to compute r of 1, 2, 1, 2. That's the only way we need to compute for this, right? So let's recall. Recall that if I look at r of L, J, and P, what this is in general is this is d by dxn, gamma L, and then what? And then we'll have we have an n, so I need a jp, minus d by dxp, gamma L, then I need an nj, jn. Then we'll have a plus gamma n, a, L, gamma a, j, p, minus gamma p, a, L, gamma a, and j, like that. And so for our two-dimensional setting, what are we going to have over here? So let's write this down. So what would so in particular, what's r of 1, and then 2, and then 1, 2, using x's and y's, right? So my n is equal to 1, so that's going to be an x derivative of gamma of L, which is x, and then j and p are both y, so y. And then minus d by dxy. It's my p over here is 2, so that's going to be a y derivative. Gamma x, and then j and n are going to be a 2 and a 1, so I'll have an x and a y. Then we'll have plus gamma of what? Now, my L is 1, and then my n over here is 1, so I can have so that's a 1, 1, so those are both x's, so let's turn those into x's, right? So I have an x's over there. So gamma of x, I can do an x, then a gamma x, j, and p are 1 and 2, so that's a y. Then I can do a plus gamma x, n is again x, and I did an x first, and I gotta do a y, gamma y, and then j and p are y, minus gamma of x. P over here is equal to 2, so that's a y. I can do an x first. I have to trace on the upper x, and then the j and the n are going to be an x and a y, and then a minus gamma of what? Gamma of x, and then p, and then so if my p is 2, so that's a y. I can trace over y now, gamma of y, and then x and y, x, y. So that's the formula we have to compute over here. So I need to find the Christoffel symbol, so let's do so. All right. So of course here my 1 component is equal to 1, right? So let's do the Christoffel symbols. So what's my gamma? Gamma of x. That's d by dx of the log of the square root of 1, which is 0. What's my gamma x, xy? That's the y derivative of what? Of the log of 1, square root of 1, which is also 0. Then finally, what's my gamma of xy? That's going to be negative 1 over 2, the x component, which is a 1. Then I need to do a x derivative of what? Of the y component, right? Which is what? Which is going to be g squared. So g squared, which is going to be what? I'm going to have a negative gx, like that. That's my Christoffel symbol over there. All right. What's my gamma y? That's the y derivative of the log of g, which is going to be a g sub y over g. What's my gamma yx going to be? That's going to be the x derivative of the log of g, which is going to be what? Which is going to be gx over g. And then finally, what is the gamma y and then xx? It's going to be negative 1 over 2 times the y component, which is g squared like that. And I got to do the what? I have to do the y derivative of the xx component, right? And the xx component is going to be what? The xx component is going to be 1, and that gives me 0, like that. Excellent. So those are my Christoffel symbols. All right, so now let's plug them in and see what we're going to get to our formula over here. So now what's my r12? r12 is going to be equal to what? It's going to be the x derivative of gamma xyy. Gamma xyy is going to be this thing over here, negative g, and then gx, like so. Then I have to do the negative of the y derivative of what? Of gamma xxy. Gamma xxy is 0, so there's nothing there. That's good. Then I have all these terms over here. So then I have this first term over here, this gamma x, x, x. That's nothing, that's 0. So I have a plus 0 plus gamma x, x, y. That's also a 0 term over there. And then I have a minus what? Then I have a minus gamma x, x, y. Gamma x, x, y is equal to 0. So that's a minus 0. And then this last term over here is going to give us what? I have a gamma x, y, y. Gamma x, y, y is going to be, so that's going to be a positive g, gx, right? And then that's hit with gamma YYX. Gamma YYX is just going to be just gx over g, so gx over g, okay? Excellent, so let's simplify this. So let's do this derivative over here. This is going to be what? This is going to be negative gx dot gx, and then negative g, and then gxx. And all those terms are 0, and then this term over here, the g's cancel, you get gxx. So that's going to be a gx times gx. The gx's cancel out, and we see that this is equal to negative g times gxx. And now I get to the R1 and 1. So what would R1, 2, 1, 2 is going to be G11 R1, and then 1, 2, 2, 1, 2. And then a plus what? Plus a G, then a 2, then a 1, 2, 1, 2, R2, 2, 1, 2, right? But this term is 0 because it's a symmetric, it's a diagonal matrix over here, and the G11 is equal to 1. So my R1, 2, 1, 2. It's just going to be what? It's just going to be this expression over here, which is going to be negative g and then gxx. Beautiful. Okay. Now let me apply this result to our metric tensor on the sphere, right? So on the sphere, what do we have? So on the sphere, our metric is what? Is ds squared is going to be d theta squared plus sine squared theta d phi squared, right? So now, of course, my g is really what? My g is really going to be sine of theta, right? So let's just tell me that R1, 2, 1, 2, and this is, of course, the unit sphere, is going to be what? Well, it's going to be negative sine of theta, and then times the second derivative of this thing, of sine, with this, so d by d theta squared of sine of theta. So the first derivative is cosine, next derivative is negative sine, so this is going to be a positive sine squared of theta. So that's the only component of the Riemann-Christoffel tensor for the unit sphere. This formula comes in very handy because it turns out that this particular structure of a metric is closely related to geodesic coordinates, right? So I'll always be able to put my metric into a form like this if I choose the right coordinate reference frame in terms of geodesic coordinates. Thank you very much.